Hi, Andrew Dunkley here. Fred and I are taking a little bit of a break over the Christmas New Year period just to catch our breath. We'll be back sometime around mid-January. In the meantime, we've been digging through the archives at some of the most perplexing and popular episodes that we've done in recent times. So sit back and enjoy.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hi there, and thanks for joining us on the Space Nuts podcast. My name's Andrew Dunkley, your host, and joining me, as always, Professor Fred Watson, astronomer at large from the Department of da-da-da-da-da-da-da-da. It's a pretty long title. That's what we'll call it from now on. G'day, Fred.
You could call me the AAL because
AAL.
Yeah, when I was astronomer in charge, I was AIC. The only trouble is AAL actually has another significant meaning in Australian astronomy because it doesn't only stand for Astronomer at Large, it also stands for Astronomy Australia Limited. So just throw that idea out. That's a rubbish idea. It'll just be astronomy. Yeah.
I was once given the title URRS. But anyway. Some people will understand that.
Yeah, you've got lovely friends, haven't you?
I've got a lot of good friends, yes.
Yeah.
Now, today we're going to talk about some very exciting things. It looks like black holes are still in people's minds, so we're going to be talking about a couple of questions that have come in from people about infinite density. Density. I keep getting it mixed up with destiny. I don't know why. It might have been a Back to the Future movie that confused me on that front. And issues photographing a black hole. Why were they issues at all? And another question about space travel and near light speed travel. We're also going to look at the cause of a gravitational wave that was detected recently. This is exciting because they think they've pinpointed an actual cause. And we're going to start off today, Fred, by talking about this rather exciting mission that's one step closer to happening, a mission to Jupiter's ice moon Europa. And that's what we'll start with this afternoon, this morning, tonight, this evening, yesterday, whatever.
Whenever it is, yeah. So look, a terrific story. Very good news from NASA that the powers that be within NASA have given the go-ahead for a mission called Europa Clipper, which is one of the missions that's been postulated, proposed is a better word, for exploring the moons of the outer planets. There are a number that are kind of on the table at the moment, some further advanced than others. But Europa Clipper is pretty well advanced, and as you can tell, its main target is Jupiter's moon Europa, which is one of these ocean moons, ice ocean moons. We believe it has a covering of ice, and we don't know whether it's thin ice or thick ice, so that will be one of the things that Europa Clipper would find out, and an ocean underneath it and a rocky core. So Europa Clipper, I think they are talking about having it ready for launch in 2023, which is, fantastic if they can do that. That's right, but apparently that's the baseline commitment, as it's called, supports a launch readiness date by 2025. It's all being done at the Jet Propulsion Laboratory in Pasadena. That's where the spacecraft will be built. So they've got the go-ahead. It's got the next step in approval from NASA, which I think is a pretty solid one. So I think you and I, back in 2025, will be talking a lot about Europa Clipper, maybe.
Yeah, what will be the basis of the mission? Are they just going there to have a look? Because
it is a bit like that, but it's a very good look. So it's not going to land on Europa. Okay. It is a proposal to going to orbit around Jupiter. And of course, orbiting Jupiter is always hazardous because of the intense radiation belts that Jupiter has. It's got a magnetic field thousands of times bigger than the Earth's and has these high energy radiation belts around it that threaten to melt the innards of spacecraft. So like the Juno mission, which is currently in orbit around Jupiter, this Europa Clipper will go into a very elongated orbit, which will give it 45 flybys of Europa. And their altitudes will vary from 2,700 kilometers to 25 kilometers. So it will really be skimming over the surface.
Oh, will.
And it's got this huge science package with all the kind of, the gubbins that you would expect to find on board something like that, including a mass spectrometer, which basically measures, the weights of atoms, as you might guess. That is interesting because Europa, like Saturn's moon Enceladus, is thought to have, although it hasn't really been properly confirmed, but thought to have ice fountains coming out of it, which are water that's squirting up through its icy shell and instantly freezing. It's snap frozen. But if you fly through it, as Cassini did with Enceladus, then you can sample what the atomic makeup is. And so the mass spectrometer will help with that. And also, it's got this ground-penetrating radar, and that's going to be crucial in characterizing Europa's crust, and revealing how much of, the potential water within is oceanic as is expected, or whether it is just pockets of water as we find in Antarctica and indeed around the South Pole of Mars.
Will they be able to tell what kind of water it is?
To some extent, they will. It may require a bit of, inference from other measurements. But if you've got samples of ice crystals, then you can do exactly that. You can basically tell whether it's saline water or fresh water, because you can measure the salt content of it. So like Saturn's moon Enceladus, which is actually quite rich in minerals, and it's the silicates in that tells you that this water was once in contact with rock. I think the Europa Clipper will be able to sample exactly those things too, assuming these plumes are real, because they're not well observed. There is evidence. I've seen images that seem to show these plumes coming from Europa. Assuming they're real, when they fly through, hopefully we will be able to tell what kind of water it is exactly.
And will they be able to tell how much water there is underneath the surface?
Yes, they will, because that will very much be revealed by the ground-penetrating radar in exactly the way that one of the spacecraft in orbit around Mars, might even have been Mars Reconnaissance Orbiter, I'm not sure, detected this lake of liquid water underneath the southern ice cap of Mars about a year ago. You and I spoke about it at length. And they can tell exactly how much there is there, because you can see the boundary with this sort of radar. You can see the boundary between an ice surface and a water surface, and that's crucial to doing this.
So this mission won't actually be looking for life, but it will be looking for the potential for life to perhaps exist on a moon like this.
Exactly. So as the blurb on the NASA website says, it will help scientists investigate the chemical makeup of Europa's potentially habitable environment while minimizing the need to drill through layers of ice. So that what they're going to try and do is as much as they can from orbit. And then, if they find lipids and amino acids and all this sort of thing in the plumes of ice coming from Europa, then clearly the next step will be a lander that starts digging holes in the ice.
Yes.
I mean, before you do that, the first thing you need to know is how thick the ice is.
Yes. If it's a couple of miles thick, we've got problems.
Actually, a couple of miles is better than what they're expecting.
Oh, is that right?
More like 25 or 30 miles or kilometers. That's right. Choose your units. So a thinnish layer of ice will be pretty good to cope with. You could probably do that. I mean, by thin, I mean less than a kilometer, probably.
Yes, but the likelihood is it's probably more, but I guess we'll have to wait and see.
The thing is, and Europa's covered in all these cracks that are brownish in colour.
Yes,
that's thought to be the effect of sunlight on brine, basically on salt water. So you've already got a hint there that it's probably a salty ocean underneath the surface.
Well, salt's probably not that uncommon in the universe, really.
That's right. It's not.
It's one of the base materials, isn't it? Of course, this doesn't guarantee they're actually going to go. This is just another step forward in the approval process.
That's correct.
Very longitudinal process, and they have to get over a lot of hurdles before they actually hit the launch button. So hopefully they're going to get there, and it's a long trip.
Yes, it is. That's the other thing.
So they've got to time it right. They've got to get in the right place at the right time.
Exactly, all of the above. That's right. So at least it's not a knockback. That's the good news.
Yes, indeed. All right. Well, we'll keep an eye on this story because I'm sure there'll be more to report in the not too distant future about a mission to Europa. You're listening to Space Nuts with Andrew Dunkley and Fred Watson. Let's take a break from the show to tell you about our sponsor, Anti-Gravity A1. Have you ever wished you could actually feel what it's like to fly? Not just control a drone from the ground, but truly experience the air around you. Well, that future has just arrived. Introducing the Anti-Gravity A1, the world's first all-in-one 8K 360 drone. And it's officially available now. This isn't just another drone. It's an entirely new category. With Anti-Gravity A1, you don't fly by fiddling with sticks. You fly with your hands and your head. The vision goggles use ultra-sharp dual micro OLED displays, and the grip controller's free motion lets you literally point where you want to go. Look left, the drone looks left. Tilt your hand, it responds instantly. It's the most intuitive flight system ever created, easy for beginners, but still offering full FPV controls for seasoned pilots. And the whole drone weighs in at just 249 grams. That means travel ready, regulation friendly, and it fits in the palm of your hand. Plus, Anti-Gravity A1 is packed with smart tools. SkyPath, which lets you design and automate flight routes. Sky Genie, which performs complex flight moves with one tap. And Deep Track, which locks onto subjects with amazing precision. The Anti-Gravity A1 is now available in 3 bundles at the Anti-Gravity store, Best Buy and authorised retailers worldwide. So if you ever wanted to rethink what a drone can be, check out the Anti-Gravity A1. Just visit antigravity.tech. That's antigravity.tech, or you can tap on the link in the show notes.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we've discussed gravitational waves before, and a few of those have been detected in recent times. The problem with them is what is the cause? And now, in a recently detected gravitational wave, they think they've got a candidate.
That's right. This is it's an ongoing story. What I like about this story is it's got a nice Australian component because there's basically a collaboration here in Australia which is called OzGrav, which is about gravitational waves. It's a kind of fairly predictable name, but it includes people from the Australian National University and I think University of Western Australia, other places which are strong in gravitational wave astronomy. So it's very nice that it has this Australian component. So what's the story? Well, the Laser Interferometer Gravitational Wave Observatory, otherwise known as LIGO, has been operating since 2015 in its sort of current state. It's actually technically called Advanced LIGO because I think it took 15 years of development to get to this stage. But they have now, not quite regularly, but at fairly infrequent intervals, fairly moderate intervals, let me put it that way, they've been detecting gravitational wave events. And for the last couple of years, they've had an additional string to their bow. Remember, there are 2 of these detectors at opposite corners of the United States, which you need, because otherwise you've got no idea where these things come from, or even if they're real. You need to see the gravitational wave pass one and then the other with the right kind of time interval in between. But they've been joined in the last few years by something called Virgo, which in fact I think it's called Advanced Virgo, like Advanced LIGO. Virgo is an Italian gravitational wave detector, and of course having 3 detectors widely spread over the surface of the Earth means you can pinpoint things much more accurately in terms of the direction in which these gravitational waves come in from.
Triangulating the signal.
Exactly, that's exactly what it is. What's interesting about this one, though, is that the signal seems to be from a black hole absorbing a neutron star. And we actually had a false alarm on this, which is embarrassing because my book has just gone to the printer saying, yes, we've observed a neutron star being absorbed by a black hole. And that I think disappeared because it turned out to be terrestrial noise. It was sort of, so I don't know whether it was a train going underneath a
microwave oven, probably.
Or, yeah, something like that. That's the usual story, isn't it? A microwave oven. That was earlier this year. And that has now gone away. But it looks as though this one might actually be the real thing, a black hole and a neutron star. We've had 2 black holes merging. That's probably been the commonest source of gravitational waves. There have been several of those. We've had a couple of neutron stars merging as well. And that actually comes with celestial fireworks that you can observe with other types of telescope, like neutrino telescopes, visible light telescopes, radio telescopes, X-ray telescopes, all of the above. And that was a big story actually late last year, if I remember rightly. But until now, we haven't had a confirmed observation of a neutron star being absorbed by a black hole, and we still don't have. It's still a bit speculative, but from the masses that are inferred by the signal, and you remember what you get is this weird gravitational chirp. It's the frequency of a sound wave going whoop, as the 2 things come together. And it's that gives you all the details of what it is that are colliding. The suspicion is it's 2 objects, one of which is 3 solar masses and the other is 5 solar masses. I think I'm right in saying that. I should check those numbers. But anyway, that is the current expectation of what is colliding. So something 3 solar masses would have to be a neutron star because it's too lightweight to be a black hole. And so that is what's making this interesting. What's perhaps a bit surprising is that you might expect there to be, once again, radiation coming from this, not just gravitational radiation, but noise in the X-ray spectrum or neutrinos, particles, things of that sort. But it hasn't been observed. And one of the Australian astronomers, I've forgotten her first name. That's embarrassing, isn't it? Susan Scott, she's at ANU, Australian National University. She says that what she says is, we've looked for light signatures of the event, but no one has found any up to this point. That indicates that if it is a black hole and a neutron star, then very likely the neutron star has been swallowed whole by the black hole. He said, and she says this could happen if the objects were of different masses. So it's the smaller object gets sucked in more quickly and is swallowed whole. So, it's not strung out into this mess of material that does emit signals in the electromagnetic wave bands. If it gets sucked in whole, maybe you don't get any signal at all except for the gravitational wave signal. It's extraordinary.
How sudden would the impact be? I mean, neutron stars, we've talked about them, and they're pretty volatile individuals and quite dense.
Quite dense is just a slight understatement there.
Yes, indeed. So I imagine it would be quite a cataclysmic collision.
Yeah, that's right. In fact, so when you've got 2 black holes, what you get at the end of it is a more massive black hole. And You're talking there, though, about, infinitesimally small points merging. Their two event horizons merge as well, and you get something called a ring down, where the event horizon itself vibrates. I think with a neutron star, you wouldn't have the event horizon, but it will be possible for the neutron star just basically to disappear over the black hole's event horizon. You don't see anything. But neutron stars themselves, as you and I have talked about many times, are active in the sense that they've got highly intense magnetic fields on their surfaces, and they beam this radiation out, which we see as pulsars. So they're not particularly quiet things.
Nope.
This thing could be a pulsar whose lighthouse beam of radiation is missing the Earth, if I can put it that way. Because the only reason we see pulsars is when you've got a neutron star whose beams of radiation from their poles actually sweeps across the Earth. And that, of course, is a particular circumstance. Maybe this one wasn't like that, and it's just got chewed up, and we haven't seen its demise other than in the gravitational waves. I think there'll be more about this story, Andrew, and I hope you and I can bring it to our Space Nuts listeners.
Our fraternity.
Our fraternity.
Yes. The more we can gather in terms of data on gravitational waves, the more we will learn, and who knows what sort of problems it could solve down the track. So,
exactly. It's always my comment that you never know what you're setting in store for the future from all this knowledge.
Exactly. Yeah. You just gather the knowledge. One day it might just go, a penny will drop with someone else, maybe a generation down the track. Who knows? It's all useful. And even if it's not, it's good to be able to gather it and one day use it some
That's
some
right.
way.
It's all these things are constantly testing Einstein's theory of relativity, and that's very important because we know there's something wrong with it, but we haven't found anything wrong with it yet. Even though it's been tested within an inch of its life, it still holds up.
Yeah, fascinating. All right.
Stuff.
You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, I do want to shout out once again to our patrons, that number 39 now. Thank you so much for supporting the Space Nuts podcast. We so appreciate it. And if you're interested in becoming a patron, you can do so at patreon.com/spacenuts. That's patreon.com/spacenuts. And thank you to everybody who has joined the Space Nuts podcast group. They number in their hundreds now, Fred. We've only had the page going for a bit over a week, and already we've tracked the century, and
great stuff.
Have over 100 people that are all Space Nuts fans who are all now talking to each other and answering each other's questions and having a fair bit of fun. So I'm so pleased that we were able to put those people together, and who knows, friendships may be forged.
Yeah, that's great.
Or collaborations that might solve some of the mysteries of the universe. Who knows? That would be a lovely legacy, I think. Let's and of course, if you would like to be a member of the Space Nuts podcast group, just find it. It's on Facebook, Space Nuts podcast group in your search engine, and yes, just ask to join, and we will click the approve button. Everybody seems to be like-minded and enjoying themselves, so that's what it's all about. Now, Fred, some questions, if you will. Hello again, fellow nutters. I have a question I'm hoping you can help me understanding. An old chestnut, black holes. If a black hole is an infinite dense point, why does it have a diameter? I don't understand why astronomers refer to black holes by their size in terms of diameter when it's meant to be a point of infinite density. Are they mistakenly referring to the event horizon? Mario from Melbourne. Hello, Mario. Thanks for the question.
And the answer is yes.
Thank you, Mario. Thanks for the question.
Mario then goes on to, everything he says is absolutely right. That if you've got a point of infinite density, it's got 0 dimensions, so you can't refer to its diameter. What you can refer to is its mass, because the mass is variable. But the fact that it has no volume means that when you when you look at the mass per unit volume, you've got something of infinite density, which is how density is defined. So Mario is absolutely right. What does vary, though, with the mass is the event horizon, the diameter of the event horizon, which you and I have spoken about before. It's a quantity that I suppose is important because if we are observing a black hole, as we did with the Event Horizon Telescope, then that's what you see. So a big one's going to be easier to observe than a smaller one. And that's why a supermassive black hole in the center of a galaxy called M87 was chosen for the first target for that Event Horizon Telescope. But no, Mario, you're quite right. It is that astronomers, if they talk about the diameter of a black hole, and that probably includes me as well, are actually really referring to the event horizon because that's the parameter. And I love the way Mario signs off by saying thanks in advance to Dave and Fred, although he does say AKA Andrew.
Yes, that one's going to stick for a while, I'm sorry to say. Thank you, Mario. Moving on. Hi, Andrew and Fred. It's Andrew from Newcastle with another question, if I may. Just watched a doco on the quest to capture the first photograph of a black hole, rather accurately the shadow of a black hole, as Fred so eloquently explained, and I didn't understand one thing, amongst others, of course. With the multiple observatories around the world and the use of atomic clocks to synchronize the data acquisition, why were they on tenterhooks regarding the weather at all the sites with bad weather at just one, putting the whole venture in peril? I understand from the show and other sources that they were collecting radio wavelength data, and I thought that this was unaffected by the weather and atmospheric conditions. I thought that was the intrinsic beauty of radio astronomy, day and night, rain and shine. Hope you can enlighten me, wait for it, but over the radio. Dear, oh dear. Andrew Broadhurst. Thank you, Andrew.
That's a great question.
Andrew, leave the jokes to me, man.
Yeah, well, I always leave them to you. So
sometimes they're good.
Oh, gosh. When was the last? Oh, never mind. Andrew's on the money there. I thought radio waves were unaffected by the weather. And the answer is that radio waves come in different flavors. And so what you might call low frequency radio waves, which are still relatively, they're way outside the medium wave band of radio and things of that sort. But low frequency in radio astronomy, I guess, goes up to a couple of gigahertz or something like that. Those are largely unaffected by weather. That's absolutely right. So that's why it can be pouring down at Parkes at the radio dish there, and the astronomers are still happily observing through that. But the Event Horizon Telescope used higher frequencies. In fact, one of the telescopes that was incorporated into it was ALMA, the Atacama Large Millimeter Array, which has featured very, very widely on Space Nuts. That is a high-frequency radio array. In fact, they have receivers that go up to more than 900 gigahertz. So that's like, nearly 1,000 times higher frequencies than what we've just been talking about. And at those sorts of frequencies, the weather plays a very important role because water vapor actually dramatically absorbs the microwave signals.
Well, and that's what experience that watching satellite television. If there is a storm and it rains heavily, the wavelengths of the raindrops can absorb the signals from the satellite and you get nothing.
That's interesting. I've never tried to watch satellite television, so that's a good thing to know.
It's one of the pitfalls.
Yes. In fact, I seldom watch television at all, so that's probably why. But the bottom line is, it's why facilities like ALMA and some of the other radio telescopes that were used to become the Event Horizon telescopes, why they're all at high altitudes. ALMA is at almost 5,000 meters above sea level. That's 16,000 feet, and at that height there is very little water vapor in the atmosphere, but you can still get weather, and that's why they were indeed on tenterhooks about the weather, because they don't want any of these. If you lose one of those arrays, and I think there were 8 of them that came together all around one hemisphere of the Earth to make up the Event Horizon Telescope. If you lose one of them, you lose a significant amount of your ability to reconstruct the image that they're seeing. And so that was why they were worried that the weather on just one of them might be moist or damper than they can cope with, and that would have screwed up the whole thing. But as it happened, it wasn't. It didn't happen, and it was great.
They got global good weather.
We did global good weather at these high-altitude sites. That's right.
Did the job. All right. There you are, Andrew. Thank you for your question. And we've got one more we'll squeeze in from John Spooth. I hope I pronounced that correctly. John, thanks for your question. Hi, I have a question that's been bugging me for some time, and I need an expert to help me out. I think we should stop there, Fred.
There's nobody here, is there? Who's that? Hang on, I'll go and see if I can find somebody.
Maybe the cat could probably answer this one too. Yeah. Now, imagine a spaceship travelling close to the speed of light, disregarding that we don't have that sort of propulsion just yet. Would the increase in its relativistic mass at some point turn the spaceship into a black hole? And if so, would that spell the end of the ship and its crew, or would they be able to slow down to reverse the process? What a great question.
It is a fantastic question. Do you want to have a go at it?
The answer is no.
It is. You got it right. Yeah, you were right on the money there. See, there is an expert. It's called Andrew Dunkley, or Dave.
So it's a 50-50 chance.
It's a great question, and the answer is a little bit prosaic, I think, and that is that in the rest frame of the spacecraft, so if you're on the spacecraft and you're going at almost the speed of light, your mass doesn't change. It's only in the rest frame of a stationary observer. And by that, I mean somebody watching you go past. Somebody watches you hurl past, and your mass gets very much higher to the observer. But to the inhabitants of the spacecraft or the spacecraft itself, your mass doesn't change.
You're still normal.
You're still normal. Yeah. So, and the same story is true with time dilation. You know that when you go nearer the speed of light, your clocks tick slower. That's as seen by a stationary observer. And so it's the same sort of thing. If you're on the spacecraft, your clock is ticking at the same rate as it ever was. But to a stationary observer, your clocks tick slower.
And this has been proven with atomic clocks, hasn't it?
It has. And indeed with mass as well. You can do this. You can see this sort of phenomenon with cosmic rays, which travel very close to the speed of light. You can see their mass change. So that's from the point of view of somebody who's not moving at the same speed. If you're moving at the same speed, you don't see any change at all.
That's pretty boring. I mean, the more we discuss black holes and the number of questions we get about them, people are really quite captivated by the strangeness of them, I suppose. They throw up all these things that seem so alien to what we consider normal. And that's because we've only experienced what's happening on our planet at any given time. So to try and comprehend enough gravity to warp time, to slow things down to the observer and increase mass, it's really whack.
It's hard on the brain, that's true. And, but look, John's question there is a great question, because it's not intuitively obvious what is happening in a situation like something traveling close to the speed of light. So he's right to ask, would that mass actually turn it into a black hole? But the answer is no, because of the reasons that I've outlined. But it's great thinking.
It is indeed. Thank you, John. Thanks for the question. Do appreciate it. Keep your questions coming in. We're trying to run them down, but it's an ever-growing mass, really.
It's all right. Look, as you said earlier, Andrew, all the space nutters are going to get together and sort them out for themselves, and we'll be redundant. I would
encourage, actually, if people want to ask questions of the group and discuss it, by all means. That's part of the reason we set up the Space Nuts podcast group. So it's a good opportunity to not only meet like-minded people who enjoy these topics, but also to maybe come up with your own ideas on what might be. And, I'll keep an eye on it. And if something pops in there that we think is worthy of further discussion, we will certainly investigate that. Thanks to everyone who sent in their questions and contributed and joined the Space Nuts podcast group and Patreon and everything else. We really appreciate it. But most of all, we appreciate you, Fred. Thank you so much.
It's a pleasure. Thank you for having me, as always.
And we will catch you next week. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thank you again, and we'll catch you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.